Hello, test mic. Okay, I can barely hear myself. I know you guys can see me. That is normal. That is expected because I'm doing a what is it called, lecture stream today, and the scientific content is Hey, my nose is my allergies is still killing me. What is this nonsense? Anyways, how is everyone? Yeah. So we are giving a talk tomorrow. So we are doing the usual talk rehearsal. My hair is a mess. Oh, by the way, I still have long hair. It's just tied back. Oh wow, it looks really bad. I need to. Yeah, I probably should have brushed it or something. Oh wow, I can hear myself on the other machine that I'm using to monitor the chat. How do I? Okay, there we go. Yeah. How do I even do this? Do we just start? I guess we know this is the wrong version, right? Where is the right version here? Here, maybe? Perfect. Okay. Okay, so what am I doing? So I'm doing this and I need a time stopwatch or something, right? Oh yeah. I guess it's also like I don't know how much chatting should I be doing because I feel like there's definitely a lot of things I can be chatting about, like World of Warcraft stuff. But I also don't know how many people are clicking into this into this video because they are actually here for technical content. I mean, I'm guessing there's like probably no one is actually doing it. Actually, I don't know because like I feel like at least one day, once this is actually submitted to a conference somewhere, then people will be looking up talks, right? So maybe I should be slightly serious today. Yeah, I mean, no, like this is going to be scuffed. Yeah, this is like beyond all what is it called? This is promised to be scuffed because this is rehearsal. But yeah, this is supposed to be a 45-minute talk. Let's see how close or far am I from the goal. So let's just, I don't know, quote unquote, without further ado or whatever, let's start, yeah. Wait, can I actually, I mean, can I? Oh, by the way, I'm started listening to this because my Oshi Kotoha does a cover of this. I usually don't listen to K-pop otherwise. You guys cannot hear, right? Yeah, you guys cannot. Yeah, you guys can only hear me. That's good. Otherwise, I'm gonna get banned off the platform. Yeah, I guess one big reason why I'm here today is because my Oshi is not streaming today. Otherwise, I usually do not be here on Tuesday and Fridays. But this is like, I don't know, I wanted to do this yesterday, but I was not ready. And I feel like even now I'm not super ready. Anyways, yeah, let's stop wasting time. Let's just actually start, yeah. Okay, so the project is on quantum field exchange. A This is a joint work with Hao at Layer Zero, is the startup, and myself at Maryland, Justin from NTT Research, and Aravind from a University of Sydney, where I'm currently visiting right now. Yeah. Okay, so a let's talk a little bit about fair exchange and what are we talking about here. Actually, this is a maybe sorry. Who goes first? Twice is a bit too much. Yeah, sorry, I'm just like still like polishing the slides and I just going through this while taking notes on what is it called. Yeah. By the way, am I low? Like volume wise? I feel I'm low. Am I? I don't really understand because like at least like I feel like this is how should I say it? Like I can definitely like not hear myself very well. Yeah, let me see. No, like I'm red. Yeah, this should be fine. Yeah, I don't get it. Also, I'm like very close to the mic. I'm close enough I can eat the mic. I remember Ina did like once and it was adorable. But anyways, yeah, let's stop wasting time. Yeah, I wasted like 1 minute, so I need to like minus 1 minute wasted time. Okay. Eh, um, so fair exchange. So this is the kind of setting that we are talking about right now. Basically, let's say we have Alice and Bob because this is the usual cryptography talk. So there are two people, and let's say Alice wants to buy something from Bob. Yeah. So Alice has some money, and Bob has some stuff. Right now it's called digital ticket, but basically you guys can think of it as maybe I don't know, either a ticket to some actual concert or just any kind of digital good. Like for example, maybe like some kind of like serial code for maybe like video game whatever things. A Yeah, like video game activation code or maybe some kind of like gift card serial code or whatever. Yeah, so basically Bob has something he wants to sell Alice and Alice wants to buy it. But then, of course, because this is a cryptography talk, now both sides can be cheating. So, for example, if Alice pays first, then if Bob is, a bad person, then he can take money and disappear. And similarly, if Bob sends first, then Alice can just, take a ticket and not pay. Okay, so this is kind of the challenge we are dealing with today. So who goes first, like who sends first? Maybe we can split this slide into, anyways, rehearsal being scuffed as always. Okay, by the way, is this, okay, this is going, yeah, let's pause for a minute, I was wondering. Okay, so the obvious solution is the trusted third party. Basically, for example, like in daily life, basically this is what you see, that you have this bank or credit card payment network that kind of holds on to money. And if Bob cheats, then well, Alice can just complain her credit card company and stuff like that, and then things are fine. Yeah, and if Alice cheats, then well, I mean the both sides can complain, I guess. Anyways, yeah. So this is, I guess, usually we have this and solution, but then there are also certain settings. There are what they call like cash-like exchange, where sometimes we are wondering if Alice and Bob can exchange directly without using this bank or card network or this trusted third party, because again, this is a cryptography talk, so people are always wondering about these questions like this. Yeah. Okay, so maybe I should still try to motivate this a little bit. So maybe there's this idea of this digital cash. In the classical setting, that would be maybe blockchain cryptocurrencies, and in the quantum setting, of course, is quantum money. There are this like cash-like setting or digital cash that people care about. So maybe I can also say like these two things. I can introduce both of them a little bit, and also say what are their similarities and differences, because they are trying to solve a similar but also not the exact same problem. But let me take a drink a little bit of my apple juice first. Very thirsty. Oh wow, that's loud. Sorry. Yeah, my mic is on top of my laptop, and my laptop is on top of the desk, and everything is hard. Like there's nothing soft here. I probably should have done something about it. Yeah, sorry, but yeah, in fact, it's not usually so loud, but then it's because I can hear myself that the anyways, yeah, it's just especially loud on my. Anyways, let's just go on. Yeah. So yeah, so I think people probably know a little bit more about like cryptocurrency or blockchain like Bitcoin, but maybe I can still say just for sake of comparing these two. So I mean, these are both like quote unquote digital cash. Um, Basically like let's say Bitcoin is like created by mining, but in quantum money situation setting you actually have a bank there, so the two are still a little bit different here in this regard. That here you still have some kind of centralized bank, and the but the security they are trying to achieve is similar. Basically, that well, people cannot spend the same piece of money twice, kind of thing. Like there's no quote unquote double spending or no counterfeiting. Like you cannot create fake money. And the in the blockchain setting, that is because there's this blockchain consensus thing. If you guys know, then it's good. If not, then don't worry about it. Just know it's secure. In the sense that people cannot do this double spending or counterfeiting nonsense. And in quantum money, there's security is given by no cloning. There's this like quantum no cloning theorem that people might have heard about, that basically makes it so that you cannot clone a quantum state. So if your money is a quantum state, then you cannot create two copies of it, kind of thing. And in terms of the, I guess one big difference between these two settings is that this transfer is that there's this like blockchain based construction, which means when you are making new, what is it called? When you are transferring money, you need to do this like global thing on network, and sometimes it takes like a few minutes before the transfer goes through, depending on which cryptocurrency you are using. But for quantum money, you just send a quantum state, so it kind of gets around one of the, I guess, usual complaints of cryptocurrency about it's not environmental friendly or whatever, that you are not spending a lot of. Anyways, that is maybe a little bit off track, and maybe we don't really know anyways because we don't have quantum computers, so who knows how environmentally unfriendly this is going to be. But anyways, yeah, that is, I guess, the differences. But back to our project, the important thing, the question that we are trying to talk about today is fair exchange. So in the classical cryptocurrency setting, there are, well, things like atomic swap, smart contract, or whatever, that basically you can swap classical digital cash. But then, because the point is just that, well, quantum money is trying to solve is trying to solve a slightly different problem of a from cryptocurrency. So these are both important things, but then you don't have fair exchange here. So maybe you kind of want fair exchange here as well in the quantum money setting, because like neither of them a kind of what is it called replaces the other. Yeah. So the point is that if there is this feature that one supports, then we can also ask if this supports the other feature, supports the same feature. Yeah. Sorry, allergies still. Yeah. Okay, so let's talk a little bit about like classical fair exchange just to get some notation, intuition, or I guess this like modeling thing, like formal modeling, because this is theory talk. Okay, so basically, formally, this is a protocol. Alice's input is her, I guess, money, and Bob's input is his money. Oh, by the way, I probably should have said earlier that the what is it called? Like this digital secret. In certain sense, I guess we can also think of it as some kind of like secret key, like you are buying a secret key from someone or someone. Yeah. But anyways, yeah, Babs has his valuable money or information or whatever. Then fair exchange says that if both inputs are valid, then you swap them. But if Bob or if either party try to cheat, then Alice just receives that the fact that, well, Bob has then Alice knows Alice does not lose her money, or at least Bob doesn't get Alice's money. Okay, so that is kind of how it always is in the classical setting. Now in the quantum setting, sorry, this allergy is still killing me. What on earth? Yeah, I can blow my nose. Sorry about that. Yeah, by the way, my chin kind of hurts because earlier I did a really stupid thing of like shaving while everything is like very very dry. Like I did not use like shaving cream or even water, and now that is such a bad decision. But that is, I guess, what we do. We are doing very scuffed things. But anyways, let's get back to a being productive. Okay, so minus 20 seconds, I guess. Or maybe more 30. Yeah. Okay, so a right, where are we? Okay. The problem is that there is this thing called quantum no cloning theorem, which means if we just take this as it is and just change this to a quantum state, then it turns out that this is actually not what you want. Because in this setting, basically, well, Alice, well, this does not go through, but Alice still has her money. But then in this case, well, there's no cloning, so Alice doesn't have two copies of this. If Alice sends one copy into a protocol and it rejects, and she just loses her money, and that's bad. Yeah, okay. So it turns out in the quantum setting, you actually want this. You want to extend this idea and say that if you are doing quantum fair exchange and it rejects, then the honest player must get her money back. Yeah, or get her input back. Yeah. Okay, that is what we want. The goal that is. So now, let's talk a little bit about the literature so far. Classical fair exchange, it's been studied for like the past 40 years. I'm not super familiar with the literature here. My co-authors are. I know that is a terrible excuse. I just need to do more reading. So this is on me. Yeah, so yes. I mean, this is also because it's still an ongoing project, so we haven't really figured out the full story yet. But anyways, sorry. Yeah. A But then on the quantum side, there is this thing called multi-party quantum computation. What they have so far, actually, when they say they, I mean also we, because I'm on the one of the papers. But basically, like what we have so far is called identifiable abort, which means if the protocol fails because someone cheats, then we at least know who cheats. So this is a few years ago by Bar Allen. Lost touch with him. I hope he's doing good. And then this is John, Kaimin, basically my advisor and my former advisor. And who is the others? Oh, Hao, yeah, of course. Wait, no. Oh yeah, yes, Hao Zhong. Basically also the same, one of the people on Quantum Fair Exchange project. So one of the authors today. And then Edge is a Mi Huang, Kaimin student at the time. Actually, Hao was also Kaimin student at the time, and myself also Kaimin student at the time. Yu Qingsheng also Kaimin student at the time. By the way, Ming just graduated, now a postdoc at CMU, and Yu Qing is still a PhD student like myself. And then this is also Kaimin Zhong and then Ming Huang, the two C and H here overlap, and Cheng Tang, I think. Yeah, yeah, also Kaimin's former student, and Zhang, I think Jia Peng or something. Means current advisor, or I guess former advisor now that she's graduated, advisor until last year. Anyways, yeah. So there's this line of literature. I don't know if I should have spent so much time like saying who these people are, but anyways, I think it wouldn't hurt, right? Because I don't have that much content to pad 45 minutes anyways. This is really stupid. Yeah, but anyways, this is identifiable board. This is publicly verifiable, identifiable board. So this is a follow-up with that, natural follow-up. Yeah. And then there is this other piece of literature, verifiable quantum homomorphic encryption from like almost a decade ago, actually. Time flies. By Alajic, also in Maryland. I was actually his TA a couple of years ago. It was a very nice experience. And then Dulac, Schaffner, and Spielman. I've never met these people, but I've looked up to all four of them. Yeah. So this is basically just an important piece of building block that both this and also our project is built on top of. Basically, or the main reason is that what I mean homomorphic encryption, right? Basically, what they call the holy grail of cryptography. Basically, anytime that you want to encrypt something and then do computation on encrypted data, well, this is what you use. And well, I mean, here this is a cryptography talk. Things are obviously encrypted because otherwise you don't want Bob to just learn at least is a money state. Yeah, and because things are encrypted and now you are doing computation on encrypted data, you need homomorphic encryption. But you also want verifiability in the sense that well, you don't want Bob to destroy at least this money state. So you want the thing to be verifiable in the sense that if Bob is cheating, you should be able to catch him. But anyways, this is all very hand wavy. We will talk more about it later. Yeah. Oh, by the way, it's complete sidetrack. Sorry, I know my like brain is like really scatterbrained. Sorry about like scheduling the stream like only like 5 hours ago. Like I probably should have put up waiting room like yesterday or something. Like, yeah, I'm just not on top of anything. But this is why it is. Yeah. But all of these have like the same. Well, I guess I mean, yeah. In fact, all three have similar problem. Basically, identifying a cheater does not return the honest party's quantum input. So when Alice lost her money, she just lost it. For example, if you use this as it is, then she, well, you guys will see in a minute. But basically, this only guarantees that well, if Bob destroys Alice's money, then Alice would know. But that is a maybe not so useful here because Alice would know either way in this setting. Yeah. But anyways, the main goals, or I guess main contributions. I don't know if I should say goals or contributions. The main point here is that maybe I should still say main goals should still be main contributions. Oh wow, clickety clackities because the mic is on my keyboard. But yeah, like the reason why we say main goal is just because it's an ongoing project. Yeah, but I think M to show is says enough. Yeah. Yeah, so we define quantum Fourier exchange for quantum states that maybe quantum states that cannot be copied is also extraneous. Now I feel like it. Maybe I can just say define quantum Fourier exchange because earlier we said nothing about this. Yeah, and also this is just true in general. And then we aim to show two complementary results. First, well, it turns out the quantum Fourier exchange is a just impossible in general with what we call classical TTP. Basically, if you have a class, even if you have a classical trusted third party, you still cannot do quantum Fourier exchange in general. But then it turns out if you have a quantum trusted third party, that is like only limited quantum capabilities that suffices. So for example, if a trusted party, uh, the wording is a little bit strange. Maybe I should also say that a also. Sorry, yeah, I know this is very scuffed, but basically the you guys can see me. Sorry, yeah, it's scratching. Yeah, hey, skin problem as always. Now you guys know the yeah. Oh, by the way, I did say I don't know if this is good to show, but actually, can you guys even see? Maybe not. Oh, you guys can see my tattoo. Oh, this tattoo is on the other hand is good. Yeah, sorry, mirrored. Oh, my neck actually seems fine. Yeah, or at least the camera didn't show it, but like the there's some like rash around my neck right now. Yeah. Um, I don't know if it's a necklace. I don't think it is because I've had a necklace on 24/7 for like months, but never had this rash. But now that I moved to, I mean, I moved, now I'm visiting Australia, I'm getting this rash. But it's also like on top of my necklace, so I feel like it's maybe half and half. I don't know. Anyways, yeah, back to the being productive here. Yeah, sorry, just chatting a little bit too much. Yeah, I mean, this is what happens with streaming and stuff, right? Okay, yeah, so, anyways, if you have a quantum trusted party, with quantum preprocessing. So if maybe I should just read this out loud, even though this is worded badly. A trusted party may use quantum state prepared before the exchange plus storage. During the exchange, it's only quantum operation is a swap gate to move stored states. Yeah, I feel like this is like worded so badly, but yeah, fine. Let me maybe try to explain in my own words and fix this later. Basically, if you have a trusted third party, I mean, if a trusted third party is fully quantum, then it's trivial, right? Because from like slide number 2. But if trusted party is fully classical, then it's not possible. So this is kind of us trying to do somewhere in between, where the trusted party is not fully quantum, but so it cannot do quantum computation, but it can at least do quantum uh, storage. That is maybe the kind of a minimal assumption. But then it turns out even quantum storage is not sufficient. Um, at least we couldn't come up with a proof, come up with a protocol that uses only quantum storage. So we relax it a little bit further to this like a I guess this like pre-processing setting that people sometimes like to think about and say that if you allow quantum storage plus pre-processing, then you have a quantum Fourier exchange. Yeah, that is maybe the actual story here. Sorry about this being worded really poorly. Yeah. Okay. So now let's talk about this. So our impossibility result. Yeah. So assuming that you have a T round fair exchange protocol pi with a classical trusted third party, and it actually does a fair exchange here, then we have the following reduction to quantum cloning. Basically, a probability of being able to clone either this or this is a at least 1 over t, with this t being T round. Yeah, okay. And therefore, because you have quantum no cloning theorem, or at least you definitely cannot clone quantum money, then this shows that you actually do not have fair exchange for quantum money. Yeah, okay. Because otherwise you can clone. Yeah, sorry, thirsty, drinking a little bit more of juice. Yeah, yeah, mention. Oh, wow. Oh, wow, I'm a little bit more gentle this time. Nice. Yeah, but I'm on the second floor of an Airbnb, and I kind of don't want to too lazy to go downstairs. So now I'm just drinking directly out of this. I'm just trying to finish this like quickly. I actually bought it just earlier, like a couple hours ago. Yeah, eh, because we need vitamin C to not get sick. Yeah. Okay, anyways, back to being productive here. So the intuition of our reduction is that we'll suppose the exchange happens in round t, lowercase t, because what I mean, if you have this like uppercase t round, then well, in one of the round, the parties must be kind of trading their inputs. Well, I mean, they can kind of like trade the what is it? Like they can, like kind of split their quantum money up and trade and like kind of send it a little bit by a little bit. But let's for the sake of a intuition, let's say in round T the thing is being sent in the sense that maybe I don't know more than half of it is being sent or whatever you want to or maybe that is kind of intuition, or maybe you can just imagine this cannot be split and just send it. Either way, yeah, let's suppose that this is sent on round T. Yeah, and you're trying to guess this round T here by choosing this at random, and you have a probability of 1 over big T of guessing this correctly. And then, if you can, then here's what you do here in your reduction. But my nose again, this allergies is bad. Wait, maybe I need to blow my nose a little bit more. It's really weird. Like something is in the air here, or maybe the air is like. I mean, we are at Sydney right now, so we are close to the ocean, so the air should not be that dry. Oh, speaking of it, I still haven't gone to the fish market yet. I really should. Like, maybe I will. Like, sometime this week. It would be nice. Yeah. Anyways, back when I blow my nose again. This is nonsense. Sorry. Yeah. Anyways, the actual reduction. Yeah. Maybe minus 1 minute again. More like minus 2 minutes. Whatever. Let's actually get on with it. Yeah. Okay, so reduction. Basically, on round T, let's pretend the trusted third party is not there. We can basically just do. I promise that there's a way to edit back consistently. But at round T star, basically you want to send at least this message, but you want to drop this other message. Okay, and then now if Alice rejects, then she must get her own money back. But then, because if this has been sent, then Bob should have accepted this. In that case, well, I mean, either Alice does not get anything back, then either Alice has nothing, and now you have unfair. So you've broken a fair exchange, or assuming a fair exchange succeeds, then Alice must get her money back, but Bob has also received the money, and now you have two copies that you've cloned. Yeah, that is maybe the actual reduction here. But the analysis, of course, has a caveat that I mentioned earlier that, well, actually, quantum states, as you guys will see later as well, quantum states can be kind of cut into smaller chunks. Or I guess I don't even need to really say that for you guys to believe it, because this is like made out of qubits, right? You can always, send some of the qubits first or whatever. Yeah. I mean, there's also like some other more tricky things you can do, which you guys will also see in the later in the talk. But now let's just, yeah. I'm just saying that these things exist, so the actual analysis is maybe a little bit trickier. I cannot just say that you guess it wrong correctly and you win. But basically, this is still the main intuition here. Yeah, I would just say brush the math under a rock and basically move on to the second part of the our results. Either let or take questions. Is anyone even watching this? Hi, if you are, I guess. I mean, well, I guess the nice thing about this format is that, well, I mean, even if you guys watch this VOD and actually have technical questions, you can just leave comments, right? Because I think I will get notified and I will be able to, what is it called? I will be able to just answer in the comments, or even like during stream one of these days, just like just say hi and ask. I guess I don't mind. Yeah. Anyways, yeah, let's move on. Yeah. So yeah, I feel like there's like not too much to, well, yeah, I mean, yeah, not too much to conclude or anything like that. Do I still have power? 31%. Maybe I need to. How about my other device? Let me check. My other device is at 44. Maybe I would just wait until I go to 20 and then I switch the charger. Yeah, so I have this like converter plug thing. Actually, I think I may have mentioned already, but that means I can only charge one device at a time. Oh wow, it went. Eh, uh, no, I think I'm just gonna switch now because it's when my screen just went like automatically darker, and that is maybe not what I want to deal with. Okay, let's see if this any better. I think it might be. Actually, am I louder now just by plugging in the laptop? It would be very scuffed if that is the case, but I sound louder. What on earth? Anyways, yeah. Actually, am I actually louder? No, I mean I'm still like red-ish. I've always been red. Okay. Anyways, yeah. Visibility, like red but not peaking. Yeah, okay. Feasibility, what we actually try to show. Okay, so probability, -3 minutes, I guess. Yeah, okay. So probability-based security. Wow, okay. I mean, I probably should waste a little bit less time, but still, like, the talk is supposed to be 45 minutes. So I feel like I'm actually surprisingly behind. Probably because we wasted a lot of time chatting and not actually staying on top of the technical content. But no, that's how streaming is, right? It's fine. We are having fun, ish. Yeah. Hey, yeah. By the way, I could have just waited a couple of days until now. I just realized now I can just show you guys my tattoo like this. Actually, I want to see so yeah, like I didn't actually have to post the shorts, but I guess why not? Yeah, I mean, good to get. I don't know. Did I actually get any views? I think I might have like gotten like 30. Anyways, yeah, I don't really care all that much. I mean, it would be good, but it would be also not gonna feel too sad if I don't. Yeah. Anyways, let's continue. Yeah. Eh, um, Feasibility. What we show. Yeah. I kind of want to go into this huge sidetrack again about like why or why not and streamer stuff, and no, I should not. Yeah. Anyways. Yeah. Probability-based security. So correctness. If both party are. Oh, maybe I should. This is a. I should first say we have uh, need to first say we have protocol. Yeah, so we do have a protocol construction. And the protocol at this right now we know it satisfies correctness in the sense that, well, if both parties are honest, then they know we have a bare minimum. But besides that, we also have this soundness, or I guess the ChatGPT or Codex calls it input state preservation, and I think I don't hate it, so I'm just leaving it as it is. By the way, the sorry, allergy swelling to my nose. Yeah, okay, so like if it's not obvious, like a lot of these slides are just built by like vibe coding. Wait 1 minute. Something strange got in my mouth. I don't know what was it. Like something like crunchy-ish. Like I don't know what happened just now. Anyways, yeah, let's actually keep going. Yeah. input state preservation, and honest party leads to a valid state. So if it accepts, then gets other party's input. Otherwise, it at least gets its own input back. But in progress, we don't know if our thing is composable. Because like in terms of like this like crypto ideal box ideal simulator is basically like very abstract things. This part we are still trying to figure out. Yeah. Okay. So the protocol sketch. So the step one is input encoding as you always have. So at least send her money to a trusted party. But then because it's encoded, now you have this thing that's under this encryption. T ink. This prefix T is you guys will know why the prefix is T in a bit, but this is the VQFHE thing that I was talking about earlier. This is this is an encryption function of the verifiable quantum fully homomorphic encryption. Yeah, okay, so I just sent him money. This box kind of encrypts it and sends it to trusted party. This is the first step of a protocol. We need to implement this box. Okay, and then we have this. By the way, now I'm just starting to realize that if somebody, like I don't know, let's say a few months down the line, this gets accepted to some conference, and somebody Googles this and find this, and actually looks, they are going to be, this is going to be so scuffed. Oh, this sounds so nice. Mercy did this? A cover of this? That's amazing. Yeah. I also try to learn this song on piano. I don't know if I've learned it well, but I think I can play it. Yeah, anyways, yeah. Yeah, I think I remember learning it. Anyways, let's keep going. Yeah. Okay, the second step of the protocol is basically this evaluation part of this homomorphic encryption. So basically, the trusted party and the Bob has to do this like homomorphic evaluation, but we cannot do it normally because normally homomorphic encryption is not a interactive, right? It's a one-shot thing. You send a thing to Bob, and Bob sends a result back, but that is bad because if Bob is malicious, then Bob just takes the ciphertext, throws it away, and then now Edis lost her money. Okay, yeah. So because of that, now you need to do this like kind of interactively, do it deal bit by deal bit, and you keep checking at every round. So this is like what we call ver eval instead of the typical homomorphic eval. This is new in our protocol. Yeah. Well, I mean not like actually new, but this is a yeah. This happens. Yeah, maybe the right way to say is that this kind of verified evaluation happens in a lot of existing literature, and we have a variant of that. We've built a variant of that is maybe similar but also a little bit different from all the other ver evals that came before us. Yeah, and the reason why is that we need to catch, well, that is not the only, well, that's one of the reasons, yeah. A reason is that we want to catch a cheating bot before, actually, is that true? I'm trying to think like for the other MPQC, if they also have very eval. I know ours before did not, right? Because ours before we just pick a server, we send everything to a server, and then we just run these vanilla homomorphic eval. The other ones, they do this like a like ring around rosy thing, with this like stinot, a yeah, like, or what is it called, the what do you call this thing, like 旋转木马 or something. Yeah, I forgot the, actually now it's bothering me a little bit. Yeah, what's the term? In English, yeah. Cursor. Okay, yeah. But basically, they do this like funny construction, right? But then they also don't do this like, I don't think they verify, or they do. Yeah, I think they kind of do. I don't like. I'm talking about DNS. Uh, who knows who, and Schaffner. Sorry. Yeah. Probably do that, right? And it's, I want to take a complete blind guess and say Nielsen, but that cannot be right. Yeah. Anyways, back to this. Yeah. Where are we? Yeah, anyways, we have very val. This is like we built our own very val. Let's just say this. Even though there are some other very vals out there, we built our own. Yeah, maybe it's the right way of saying it. Is that right? Yeah, good enough, I think. Yeah. Is it good enough though? Nah, I shouldn't get hung up on this. I can, yeah, discussion, ver, eval, new, or what? Yeah, because like this cannot be like, I don't think this is new. I don't want to claim novelty here. Yeah, but anyways, yeah. So, let's talk about building block. Sorry, I blew my nose again. I don't know if this is I feel like this hardware mute is at least a little bit better than the one before. Like the one before, when I try to press it, it's a very loud noise. But now I think for whatever reason I can press this hardware mute without making it very loud. But anyways, yeah, QEC, quantum error correction, one of our building blocks. Basically what you obviously need for this kind of protocol, because I mean Bob can always cheat, Bob can always throw stuff away. So you want this kind of error correction protection by saying that, okay, now you can cut the state into a lot of copies and you can do some, but then as long as you don't lose too many, then you can decode and get the original thing back. I probably don't know if I wanted this, but yeah. Maybe that is fine to say as a remark. Basically, this is all entangled. This is not just an independent copies because there's no cloning. You cannot just make uncopies. Blow my nose again. Sorry, scoff. But yeah, the actual mathematics is basically same here, right? That you have encryption and then you have some attack, you have decryption. Uh, Maybe write this as compose. Uh, yeah, I think compose is easier to read than this. But anyways, yeah, this is a encode, attack and decode gives you an original state. If this is low weight, yeah, you can pick lambda. The bigger lambda is, the more things you need to cut into. Yeah, the more a physical qubit you need to cut into. Oh shoot, maybe drop a physical terminology, even though that is standard. Maybe no need for our audience tomorrow. The talk is tomorrow. This is so scuffed. But yeah, anyways, transversal operations. Turns out that the this kind of QECs, they are homomorphic in some sense. Like a basically C naught is just one of the quantum gates, because we always like to talk about quantum circuits. This star is input output table, and it turns out that the this thing is naturally homomorphic over C naught, in the sense that if you have this, like this is encoded, and you hit the entire thing with a C naught, that is the same thing as you first do a C naught and then you encode it. So this two thing kind of commutes very cleanly, and this is kind of just the corresponding picture that you have this C naught gate on all copies, on all. Maybe I should just say physical qubits. Maybe this is fine. Yeah. Okay. Yeah. So basically, just do this. Yeah. That way, it's named C naught because control naught, like control flip, because you see 0 means the second target has no change, and 1 means the second target has picks up a negation. That's why it's called C naught, control naught. Yeah, okay. So now, back to this. I mean, not back, I mean, we're always here. We did not get distracted yet this time. Until I distracted myself just now. But okay, yeah. Now quantum authentication, or a what we basically say the source of our verification. Yeah, this is basically where the verification comes from. I should first say what is this? What is authentication? Here's the interface. Uh, yeah, I think interface is the right word here. basically you have what is this? Like maybe use more QAS need maybe a more standard KG in deck framing. Yeah, this kind of thing has to be framed a little bit better. But anyways, yeah, I should say that this is standard terminology. A QAS is of course a keygen, an ink, and then deck. Yeah, so you run KG keygen, and then you do ink. You send a thing to a server. Server might have done some attacks and then sends it back, and then you do deck, and then you either accept or reject. If you accept, then the security gives you this. Yeah, a bottom maybe a security is this. Yeah, I want to say the security is this. Yeah, okay. Now, a background trap code, more background of course. This is just one of the QAS. I mean, all of this is like just background, so I know I'm talking about it in a very bad, disorganized way. But maybe this part is a people who know already know, people who don't probably don't, and I don't know if I want to spend this time much time on a background anyways. But here goes nothing. A n is number of qubits. Sure, yeah, why not? Actually n is the same n as before, so we probably don't need to say. Yeah, define of n is a bit strange. Yeah, okay. And then you do key generation. Basically you pick a random permutation, and then you pick one-time pad. And then the encryption is basically that you just do a quantum error correcting code here, and then you append a bunch of what they call traps. That's why it's called trap code. And then you do you kind of permute this so the bad guy doesn't know where are the traps and where is the data, and then you encrypt it. So the bad guy cannot just read. Yeah, okay. And then the intuition is that if the bad guy wants to hit your data, then he will certainly accidentally hit some of this, and then he will be caught. Um, Otherwise, if this is clean, then you can assume that then the math tells you that this is mostly clean as well. Like if this is perfectly clean, then this must be mostly clean at least, if not perfectly clean. And if it's mostly clean, then you can because it's under quantum ECC. Queuing is from before quantum error correcting code, so you can decode. Yeah, and that is indeed what we do here. Basically, decryption is that we just decrypt, and then we just kind of peel all of this away, and then we measure and check this. If this is bad, then you reject. Otherwise, you just just decode this and you get a state back. So this is the trap code here. It is a QoS. Yeah. Okay. Finally, a VQFHE is a homomorphic evaluation over trap code. That is what we, so this FHE, the encryption, basically just borrows the trap code encryption. So what you do here is, but basically the interface is similar, or maybe that's a bad way of saying it. Fine. Maybe I can say that I should just go back to say that this is a security game. Basically, that the next step is to go from trap code to VQFHE. So before I go there, maybe I should say a VQFT2, maybe a what is it called? Need a KG Inc. Eval and deck framing as well. Okay, so now we want to say that, well, now you do a keygen, and then here's the, I guess, kind of a picture of how this kind of thing is used, and then you encrypt a state. I mean, this is asymmetric now, so you have public and secret key. You use public key to encrypt, and then you send this. Don't you send the public key over? You definitely want to send the public key over. Okay, so you need to send public key over, otherwise you cannot eval. Yeah. Okay. Or I guess you can just kind of fine. You can assume everyone has public key. Why not? Yeah. Let's no. You want to send public key because otherwise this makes not so much sense because you cannot assume everyone has this because it's quantum. Okay. Yeah. Quantum public key. Okay. Yeah. Whatever. You send this over, and then you do a eval, so you get some output, you get it back, you decrypt, and then you either get some output or reject, and the security says that if you accept, then this must be close or basically equal to this apply on. Basically, this should be the your target computation. That is the what the security gives you. Yeah. Okay. So how do you build this? Well, the idea is to just basically find homomorphic operations on trap code. Okay, so for example, let's say trap code actually naturally gives you homomorphic C naught. So let's actually see if that why is that true. Well, let's say you have trap code, then well, I mean, what I mean by homomorphic C naught is you literally just C naught everything, and I claim this will work. So this picture is basically just saying that okay, yeah, both have the same permutation pi, and one-time pairs are independent, so they are encrypted. Yeah, I mean of course. And then so we are saying same hidden permutation means the data lines up, so the data are in the same slot, and the traps are in the same slot. So things line up, and then that is what we have. Maybe independent OTP is a C naught is here. I don't need to say maybe don't need a independent OTP. A takes away a breaks the flow. I mean this is a true fact that is maybe that we use, but we don't need to really say. Yeah. Okay. So now we have the we want to prove that this actually works as advertised. So you have this, which we just write this out is this, and we have this. We also just write out is this from before, and then yeah, this is a sure a oh yeah. I think this is fine here. We don't need here. Yeah. Okay. Sorry. Yeah. So you hit everything with CNOT. Now the because this is what they call Pauli, what is this what they call Clifford. If you know, you know. If not, that's fine. But basically, you can just kind of swap the order, and then this picks up an extra offset, but that is fine. Yeah. And then you say, okay, yeah, this is the same permutation. So because everything lines up, so you can just swap it. Doesn't really matter. Yeah, because you know the picture from earlier, like if you do this CNOT, everything is data lines up with data and trap lines up with trap. So that's why you can do this. Okay, and then a logical CNOT basically CNOT is homomorphic over QEC as we established well as we claimed earlier. This I did not give a proof earlier. Maybe earlier I should have stressed that I did not plan on giving a proof. This is just something that we are all willing to that I'm hoping we are willing to assume. Yeah, and then the traps untrenched. Oh, instead of text untrenched, I should say traps untrenched. Untrenched or unperturbed. I don't know, something like that. Yeah. Okay. And then now, but this is only C naught. If you want a universal gate set, then this is where you actually use a paper. Yeah. Okay. But yeah. Okay. So now that is basically all the backgrounds. Now we are finally ready to talk about our protocol. Okay. So our protocol basically, first of all, the input encoding. So a construction one maybe have to say input encoding. Yeah, so input encoding protocol, basically the idea is that the trusted party has prepared this thing, and then since the first half instead of one half, I should say the one half should be first half unencrypted half. Yeah, so it sends the unencrypted half of EPR to Alice, and then using APR, Alice teleports this, and trusted party gets this. I know this is very hand wavy, but this is just how it is because quantum teleportation is. I'm just using as a subroutine here, but I can quickly say why this must be built this way. The what is it called? A The point here is that Alice must be malicious, but not must. Alice might be malicious, so you cannot let Alice do her own T-Ink. So you must keep the T-Ink half on the TTP side all along, and then you are only sending the other half to Alice so she can teleport, and now you get this clean, like correctly applied T-Ink. And the underlying state can be chosen by Alice using teleportation. Yeah, okay. And then now maybe next step is the maybe instead of one check gate, maybe homomorphic application. Homomorphic gate application is maybe the better way of put it. Yeah, okay. So now you have some gate G. Maybe this is a little bit too much, especially because this is yeah, there's a lot of yeah, especially because earlier we just have the C naught being the what is it called? Yeah, I think I just we just should not say what is this. We just say we have some symbol G that we are applying, and this is something that looks like trap code. Basically, you have a piece of your QEC, and then you have a trap, and then you have uh, you have two pieces of traps. Yeah. But the idea is that you are only doing one piece at a time. You cannot send the entire QEC code word to Bob because otherwise Bob drops all of it and you are very sad. So you are taking one piece out of your QEC, you mix it with some traps, and then you send to Bob. And Bob applies some gate, sends it back. Yeah. And then now you need to measure this, except you cannot measure because you are classical with quantum storage. You are not quantum. And because of that, now you need to send this, which is, well, I guess this is now this. You need to send it for Alice to measure. But here you are worried that Alice might cheat. So here you want to append another trap for Alice. So now you have this. You send this entire thing for Alice to measure. And similarly for this, you get this. So after Bob does his thing, you have this, and then you append this so this part is to protect against a malicious Bob, and this part is to protect against a malicious Alice. You mix this to and then you send to Alice. Alice measures both of them, send back the result, and then by the way, this G dagger is just G inverse. It gets rid of this. Yeah, and then now you keep the measurement. You check the measurement outcome. If the measurement is all correct, then now you have this G of DJ, which means you've successfully applied a gate on this piece of QEC, and now you repeat this for the entire QEC, and now you have a gate. Or either that, or you need to, if a trap is no good, then of course you need to do some more careful bookkeeping. For example, if this is wrong, like if the measurement outcome of this is wrong, then you immediately know Alice is cheating. If the measurement outcome of this is wrong, then you don't know who is cheating yet. But if this is wrong all the time while this is correct, at some point you will be able to conclude that Bob is cheating by doing some statistics. Yeah, okay. So that is kind of why it is, the intuition. But it turns out we're not done yet. because it turns out that there is this re-encryption thing that we need for the sake of our analysis, what they call polytooling. But if you know, you know. If not, then you just think of it this way: let a actually, let me drink a little bit of. Do I drink tea or do I drink apple juice? I kind of want to drink both. Apple juice because tea lasts for a little bit longer. I think. I don't know. Okay, where are we? Well, we wanted to say that a basically, yeah, I feel like this part I haven't really thought about as carefully. But basically, a in cryptography, this is such a sweeping statement that is maybe not so nice. But fine, I would say in you know what, in cryptography, why not? Like, come at me. You know what? Yeah, like no, the well, what do I even say here? So yeah, maybe I should just say often. Often there will be benefits in kind of stacking encryptions on top of each others or kind of refreshing your encryption keys. And that is what this is doing because it often makes things easier to analyze. And this is kind of what we do here. Basically, this is already encrypted. Or it should be. Why is W not encrypted? Wait, is it actually not encrypted? Because if it's not, then it should be, right? A we need to like change this to the more what is it called? Yeah, this is not conventional, but W should be encrypted. I mean, this part is encrypted, but it's unclear if this register is, and it should be if it's not. Yeah, so we should maybe just just the conventional what is that Q first or pi first? Yeah, it's Q and then pi. Yeah. A Q pi instead of this a cat x a yeah, maybe we should say this. Yeah, I think that makes the story a little bit well, more correct. But anyways, so now we have a what is it? A yeah, anyway, so the thing is already encrypted, but you want to just encrypt it again, you see? So this is encrypted, or it should be, and then now you are stacking encryptions on top of each others. Or one way to think of it is that you are decrypting and then you are re-encrypting. I mean, that is different. I'm going to sweep the differences under a rug, but this is kind of important for analysis. The analysis that I will not be able to talk about today, anyways. But anyways, yeah, there is a this kind of encryption move that you are asking Bob to do. Because you think Alice must be malicious, so you are asking Bob to re-encrypt for you, and then now because of that you have this R floating around everywhere. But that is fine. Yeah. That is kind of how you apply a gate. Now, uh, to uh, to apply a staircat, the intuition is that you just apply every gate, and that is kind of what you do here. You have a for loop here, but it turns out that that is not fully enough. The problem, the I guess not from the yeah, fine. The problem being that well now you have Bob re-encrypt, but well, what if Bob is malicious? Then you haven't done enough yet because it turns out that you also need Alice to re-encrypt against a malicious Bob. So this is kind of what you do here. So you have this as this, but then you want to flip this around, have the two-party change roles. The colors doesn't match. This two should be blue and this should be yellow. Yeah, maybe I should a what is it called? A yeah. Uh yeah, maybe this should not be there should not be a background here. or maybe these two boxes should be the same color, or this should not overlap with these colors, and these two colors should be blue and this should be yellow to really show that this is a mirror image of this. Except here you are applying identity gate, so you are not actually doing anything to your data, but you are but you have this mirror image. So like the underlying plain text is the same, but now you also have here you have Bob re-encrypt, but here you also get Alice to re-encrypt for every gate, and that is the entire circuit. Oh wow, this is I shouldn't get so mesmerized. Wait, this is no, I shouldn't say it. Yeah, okay. Yeah, sorry. This like past life is stuff. VTuber 困惑 taboo thing. Anyways, yeah. Yeah. I mean, open secret, so who knows, who cares? Yeah. You know what? Actually, I don't know this song. Probably means like one of these days I can listen to it a little bit more. But for now, I feel I don't understand it enough to really. Oh wow, her final thing before she left, well, Konko left, she did more. That's not the one. This like VTuber past life reincarnation stuff, should we? Yeah. Anyways, okay. So to get everything into one big protocol, finally, so we do input encoding. Both inputs go to trusted party, and then we run this for the first circuit to check if Alice's money is right, looks right, input looks right, and then we do same with Bob's thing, and if both of these pass, then if both accepts, then trusted party exchange the sends the money to everyone. Otherwise, trusted party returns everyone's inputs. That is the kind of how the protocol goes. Yeah. Okay. So to summarize everything, now we have feasibility for quantum trusted third party. All quantum resources are independent. We can just quickly maybe result two lines too much, because I feel like these two lines are saying like has too much overlap. But anyways, yeah. So trusted third party prepares this, is input independent, and then also prepares a what is this? Oh, VQFH evaluation key. Yeah, which I brushed under a rock earlier, but this are a thing. Yeah, a yeah, maybe I will just keep brushing them under a rug, but you need to prepare this, and you also need the. I mean, it's in the gate evaluation thing. The basically you need to universality thing, like this is not universal unless you have this. Yeah, unless your circuit is compiled to take extra inputs. Yeah, maybe that is the maybe that's the right way to say it. Yeah, maybe that is good enough. I can just say that sentence, right? That, well, we need this because the gate set you have is not starts out being not universal. But if you wanted universality, you can compile the circuit and take some extra inputs here, and then what's this Q0? Hey, should just use a T ink, right? Yeah, let's just say T ink. Yeah, why not? I mean, sure. Yeah, so you take extra inputs and now you're universal. Yeah. Okay. And then you have traps, you have more traps. Yeah. Okay. And because of that, now, if you prepare all of this ahead of time, then online you have this. And then you also do some classical trap checks, like check measurement outcomes. And you also need to like do a bunch of key updates because you are re-encrypting all the time. So of course you need to do bookkeeping. That is kind of it. Yeah, okay, so that's all we have. Thank you. I mean, I don't know if there will be any questions here. I mean, you guys can, of course, say hi or say anything, either now or in the comments below. Yeah. or also, or ask me next time I go live or something. Yeah. Hey, I'm kind of tempted to stay and kind of work on the what is it called, the slides, but I feel I should not. Like I should still fill this a yeah, no, this one, yeah. Wait, actually, whose cover is this? Oh, this is original. Wow. Okay. Right, right. Because he also sings. Yeah. Anyways, yeah. Where are we? Yeah. I feel like I should still like keep this VOD relatively clean, even though it was already very scuffed. It would be very. I don't want to turn it even more scuffed by appending like another 2 hour or two of me working on this, like iterating on the slides. So I think I'm just gonna call it here. So thank you all very much. I wish me luck for the actual talk tomorrow. I mean, this is like a what is it called? I mean, I don't know how many minutes am I subtracting, right? 5. I know I wasted a lot more than 5 minutes here, but I mean I only recorded 5 minutes. But I mean I hope I don't go over time tomorrow because like this thing is supposed to be 40 minutes. I mean 45, but I should leave 5 for a Q&A. Yeah. But anyways, yeah. Thank you all. I will see you all next time. Oh, yeah, I mean, probably for World of Warcraft, right? Actually, it's a patch. Like, when is a patch? I feel I should know. Ah, so the patch is really soon. I think I will try to kill the Nemesis on stream. Uh, including the Fable, let me solo him. But I think only single question mark comes out, right? So I feel like in the next couple of days, I will still stream myself try to kill the single question mark version. Yeah. Anyways, thank you all. I will see you all next time. Yeah. No, I need to do like ending screen.